Welcome back to CUPR 2020 tutorial on cycle consistency and synchronization. I'm Qixin Huang from UT Austin. So I will cover theoretical aspects of cycle consistency and synchronization. So this lecture is divided into two parts. In the first part, I will talk about the theory of optimizing maps across a collection of objects, focusing on optimization and exact recovery conditions. In the second part of talk, I will briefly mention some of the recent works on joint learning of neural networks. Here we treat neural networks as maps between different domains. Let me begin with some motivations of map synchronization, namely when computing maps between geometric objects, what are the benefits of optimizing together across a collection of objects? So I will walk you through two examples. The first example is solving puzzles. In this case, a specific example is assembling fractured surfaces. I believe many of you have solved a few such problems in your life. In this case, we have two fractured surfaces. The challenge is that on the surface we cannot extract features to match, right? So in this case, how to address this issue? Like what most of us will do is to look at additional clues, right? For example, in this case, without additional clues, there's just so many possible assemblies, right? You just can't differentiate them. So what about if we have a third piece? In this case, we have a very salient match between the third piece and the first piece. And that match also gives us a way to match the second piece, right? So in this case, we have a very concrete match, okay? Very concrete match. This shows that when building maps, right? So in this case, it's a rigid transform between two fractured surfaces. It's beneficial to include additional objects. The second example is closely related to the algorithm we are trying to introduce. So here again, we have two objects, right? Two 3D objects here. And our goal is to build dense correspondences between them. So in this case, what we do is that we go to the internet, we download some software, and we press a button, boom, and it gives us some result, right? In this case, unfortunately, because those two objects are very different from each other in terms of geometric shape, this particular algorithm returns some incorrect correspondences that are colored in red here. Right, so what we can do here, obviously you may say, oh, let's read the paper and see an algorithm, try to improve the algorithm and tune the higher parameters. But what about this is impossible or too tedious to do? I give you one very simple strategy to address this issue by using data. What we can do here is that we can find intermediate objects whose shape sits in between the first two objects. In this case, we don't need to improve the algorithm. We just run the same algorithm, right? Even you don't understand the algorithm, run the same algorithm twice, right? First between the first object and the intermediate objects, and then between this intermediate object and target object. In this case, the same algorithm, the same software outputs two good maps, right? Because source and targets are close to each other. And because of that, what we can simply do here is just compose these two maps into a much improved map between the source and the target. Okay. All right. Okay, so what happens here is that we can have a slightly different angle to look at this, is that if we think about a collection of objects and we have a black box software for computing maps between pairs of objects, right? Clearly, some of the maps will be good, some of the maps will be bad. My argument here is that the network of approximately correct maps still form a connected graph, right? So if this is not the case, you can simply insert more shapes into the collection so that each shape is surrounded by similar shapes where this existing algorithm can handle, right? In that case, eventually you can have this kind of a network of correct maps. Of course, you don't know what maps are good or not. And this will really introduce the map synchronization problem. Okay, namely we have a net of I have a net of network of objects where the nodes, objects, and edges are maps computed between pairs of objects in isolation using an existing algorithm. And our goal is to identify the good maps, right? So suppose we can do this, then we can use the propagation idea to get good maps between all pairs of objects. Okay. Of course, we need some additional signal, additional supervisions to make this possible. Thankfully, if we consider a network of maps, there's natural constraints essentially says that if you compose maps on a cycle, and then you should get the identity map. Okay, so this is something that is true no matter how the maps are represented. It applies to rotations, applies to dense correspondences, and also, as Leo mentioned, it also applies to functional maps. Okay, so in this case, the toy example, we have if we consider 3 maps computed between pairs of objects in isolation, then they are inconsistent, right? So they're inconsistent. If we replace the bad map by the composite map, then they are consistent. Okay, they are consistent. Okay, the cycle consistency constraint is simple to state, but difficult to formulate. Okay, so in the literature, in fact, the literature is about 2 decades. Okay, people have tried using different strategies, right, to formulate this cycle consistency constraints to perform map computation. Okay. Okay. So the challenge here is that whenever you find an inconsistent cycle, you know that at least one map is bad, but you cannot locate it. Okay. Okay. So the existing literature falls into 3 categories. The first category is about spanning tree optimization. So the idea here is to optimize the spanning tree so that they induce the consistent maps. Okay, here a consistent maps can be induced from a spanning tree, and we want to optimize the spanning tree to maximize some global score. Okay, I should argue that the spanning tree idea is closely related to the low rank formulation we will introduce. But the difference here is basically how we actually represent the maps and how we perform the optimization, namely map representation, right? Just as functional maps have been very successful as a map representation for computing maps. So I want to emphasize that. So this is also true in terms of how we formulate the optimization problem for synchronization. Okay. So in this case, even though spanning tree is a concise encoding of consistent maps, so the way to optimize the spanning tree, because we don't really have very powerful tools, right? So there are exponential number of spanning trees in a graph, and we don't really have a global optimization strategy to navigate through all the spanning trees. Okay. Oh, so those methods are greedy. They don't have theoretical guarantees, and their empirical performance is limited. So the second category of methods applies global optimization. That is the advantage. But on the other hand, the formulation is still limited, right? So the key idea is that we are trying to sample inconsistent cycles in the graph. Then we are trying to remove a subset of edges so that all the inconsistent cycles, contain at least one edge that is removed. Okay, so this is one example where we are trying to formulate an edge selection problem so that we break all the inconsistent cycles. Okay, so those kind of approaches generally work better than the greedy approaches, but on the other hand, the challenge here is how to sample inconsistent cycles, right? So because there's just an exponential number of cycles we have to sample in the extreme case. So the real breakthrough comes from the third category of approaches. So this is also motivated from the compressive sensing. Okay, in fact, we can have a compressive sensing view of map synchronization. Concretely speaking, the cycle consistency essentially says that one map is the composition of the other, meaning that if we consider consistent maps as a signal, this signal is compressible, right? We don't need to store all the maps. But on the other hand, the input maps compute between pairs of objects in isolation. They can be considered as noisy observations of the good maps, right? Some of the correspondences are good, some of them are bad, right? So noisy observations. Now we arrive at some familiar setting where we have a compressible signal, and we have noisy observations of this compressible signal, right? So this sounds like something that have been happening again and again. And what people in the applied math and signal processing communities they do is that thinking about how to formulate this as an optimization problem. So how to do this in the map case is that we can think about first of all represent the maps as a matrix, right? Either as a rotation or 4x4 transformation, A-form transformation, or in this case, when considering dense correspondences between geometrical objects, we can encode maps as permutations. Okay, or in other words, 0-1 matrices we handle in partial maps. Okay, and as what Leo mentioned, we can also encode maps using functional maps. Okay, if we encode maps as matrices, if we have a collection of objects and maps between pairs of objects, then we can think about this kind of data matrix X that encodes pairwise maps in blocks. Okay, pairwise maps in blocks. So this is a big matrix, it's a block matrix. So the nice thing about this matrix is that first of all, the input maps are simply noise observations of individual blocks, right? So we may not have a full observation or partial observation. So another nice thing about this is that we can show here is that the maps are cycle consistent if and only if X is no rank and if only if F is positively semi-definite. Okay, so here, so basically they're equivalent. Okay, so the positive semi-definite property is kind of surprising, but on the other hand, so here we enforce that the elements are 0 and 1 binary matrices, right? So with this kind of integrality condition, you can show that they are equivalent. So this is really a nice view of that combines the graph theoretical properties like combinatorial constraints such as cycle consistency. On the other hand, we have a matrix representations of maps, and the cycle consistency is equivalent to some simple property, positive semi-definite, something that sounds very familiar if you are familiar with convex optimization. So this motivates us to the following formulation for permutation synchronization. So what we have here is that we have some observations along graph G. G is essentially the nodes of input objects, and we have an edge here if the edge is touched to a map, which is encoded as xij input. So xij are essentially the maps we are trying to recover. Okay, so essentially we are trying to make sure that the recovered map is close to the input because the input contains information. We are using L1 node to essentially address noise. Okay, so the constraint here essentially we have cycle consistency. In here we have formulated the positive semi-definite, right? So this is a very this is a convex formulation, and we have to do some relaxation, right? For the permutation matrices, the discrete is not a convex set, but we can simply take its convex hull, which is the space of stochastic, doubly stochastic matrices, right? So that is a convex set, and then the resulting formulation is called semi-definite program, where we know how to solve efficiently. Okay, all right. So we know how to solve it efficiently, computationally wise. And another advantage here is that we can really understand, analyze for example, how much noise in the input we can tolerate so that we can remove those noise, right? So this is a very exciting news. In fact, we can show that given noise input maps permutation synchronization using SDP, we cover the underlying maps if the incorrect correspondence of each point, meaning that for each point, it has correspondences input to other points. The fraction, how many correspondences incorrect? If we count the maximum one, is smaller than number 2, which is the second smallest eigenvalue of the graph Laplacian of G. We keep in mind that G essentially is the graph that specifies which pairs of objects have maps. Okay, so number 2G is algebraic constant divided by 4, right? So if the incorrect number of correspondence is upper bounded by this, then solving SDP removes all the noise. Okay, so that is exciting because it essentially says that if we have a good network, right? So and the fraction of noise is not that big, then solving SDP is guaranteed to remove all the noise. Okay, keep in mind here that so here we assume the noise are adversarial, right? They can be consistent with each other. Okay. In fact, later we'll show an example why this is consistent optimal. So in fact, this bound you cannot improve. Okay, it's not hard. It's very difficult to improve, and in fact, it's optimal when the object graph G is a clique. Okay, so in this case, number 2G is the number of vertices. If number of vertices divided by 4 it means that we can tolerate 25% of incorrect correspondences. Okay. In fact, that this is the best help you can have, right? So we have a worst case scenario where we divide the objects into 2 clusters, right, of equal size. And so basically within the clusters, all the correspondences are correct. And between the clusters, half of them are incorrect. But they are incorrect in a consistent way, right? So in this case, we have 50% of intercluster correspondences and 50% of the incorrect, right? They're incorrect in consistent way. And we cannot decide between correct, right? Because the 50 versus 50, so that we cannot improve, okay? Meaning that essentially in the adversarial case, where the noise are consistent with each other, 25% incorrect ratio is the best you can help. Okay. Of course, if we assume randomness, we can certainly improve this bound. Okay. So another interesting aspect here is that if we want the graph to have denoising power, number 2G, which is sometimes people call this algebraic connectivity of the graph, is something that you should maximize. Okay, in fact, this is what has been the strategy that people have used to for constructing the input graphs. Okay, input graphs among the objects. So far we have considered adversarial noise. If the noise follows some pattern, in particular shows some randomness, then we can tolerate a lot more noise than in the adversarial setting. So formally speaking, this is we can consider the so-called generous address running model, which is established model for studying no-rank matrix recovery techniques. Right, so this model is controlled by a few hyperparameters. So we have P-observe that specifies the probability that 2 objects connect, meaning that the density of the pairwise maps in the input. P2 is the probability that a pairwise map is correct, and incorrect maps are random permutation, right? So we assume that they're independent. So you can consider this as a benchmark. Of course, in practice, the noise model is a lot more complicated than this. Later, we'll talk about some learning approach that seeks to use a neural network to capture to learn the noise pattern. Okay, so that we'll discuss later. But in this case, we analyze the permutation synchronization under this established generalized at the surrounding model. And we can show that, in fact, that the P2, which is the probability that the pairwise maps is correct, and it only needs to be slightly bigger than a constant times some polylog factor divided by square root of n, right? So when the number of objects goes to infinity, then P2, this lower bound, can also go to 0. Okay, so meaning that so this is something happens when the noise random. Okay, so you can also show that for example, when m is a constant, meaning that number of points per object is a constant, then the exact recovery condition is a polylog factor from the information theoretical limit, right? You can show one can show that no method works if P2 is smaller than a constant divided by the square root of n. Okay, so this is called a near optimal algorithm. So an interesting fact here is that for recovering low-rank matrices, we can use the so-called robust PCA, right? So that is a well-known technique, right? But if we run the RPCA and permutation synchronization and compare them for maps, you can see that the permutation synchronization works a lot better than RPCA. Okay, a way to understand this is that RPCA can handle dense corruption if the perturbations exhibit random sign pattern. Yet, for example, if you consider the underlying ground truth identity, if we take the expectation of the sign of the elements in terms of xij minus identity, then the expectation is not 0. Okay, it's not 0. Okay, meaning that this explains why RPCA performs suboptimally for this particular problem. But what happens in our case is that there are map constraints, right? So basically, each block has to be doubly stochastic matrices, and those map constraints include a quotient space defined by K. Essentially, it collects all the matrices where the row sum and the column sums are 0. And this quotient space, then you do the expectation again, then the sign becomes random, right? So this really explains why this permutation synchronization, by adding those additional constraints, is critical for achieving information theoretical optimal rates. Okay. So far we have talked about permutations. An interesting question here is how to handle partial maps. So in a follow-up paper, we showed that we only need to modify the formulation a little bit. So in this case, we modify the objective function as follows, right? So the diagonal block of cell identity, but off diagonals we cannot never enforce that it's doubly stochastic matrices. But on the other hand, we formulate the formulation by augmenting the matrix X using by one row and one column. So here M essentially is the expected size of the universe, meaning that how many points the underlying complete object has, and the input is essentially partial observations of this complete object. So what we can do here, right? In other words, it's the size of the universe. So what we can do here is that we can apply spectral method on the input to estimate M. And we can show that this provides a very reliable estimation of M. And then given M, we solve augmented SDP, and we can show that under a modified randomized model, we have n objects, universe size is M, right? So each object contains a fraction p set of M elements, meaning the expected size of objects is p set times m. Okay, a p set, of course, is a value that is smaller than 1. And again, each pair is observed with probability p observed. Each observation is randomly corrected with probability 1 minus p2. Then we can show that the underlying maps can still be recovered with a similar rate. So p set squared, right, is depends on the overlapping ratio, right? P set, if p set is small, then the expected number of correct correspondences between a pair of objects is small. So in this case, the p set squared is expected, because if it's small, then the p2 has to be big, right? The rest is very similar to the case of the having complete objects, right? So the permutation case. So in this sense, this is also considered near optimal. Okay. So far we have talked about the semi-definite programming formulation, which is derived from the equivalence between the cycle consistency and the fact that the matrix that encodes pairwise maps in blocks is positive semi-definite. Okay. But there are many other optimization techniques, right? So for recurring, in fact, another equivalence says that is a no-rank matrix. So in this regard, there are many other optimization strategies for recurring the underlying ground truth map. For example, one widely used one is called spectral map synchronization, which is very. So the intuition is the following, right? So we can decompose X observation, which is the input, as the sum of the X ground truth plus some perturbation, which is encoded in X noise. Then the David-Kahan theorem essentially says that the leading eigenvectors of X observation, that is what we can compute, and the leading eigenvectors of X ground truth, that is essentially you can use this to derive the correct maps. So this is upper bounded by the norm of X noise divided by the spectral gap of X ground truth, right? So if we have a low rank matrix, the spectral gap is very big. So meaning that on the right hand side is essentially the upper bound on the perturbation. Of course, here we use the L2 norm of the leading eigenspace. And in practice, we have for a particular algorithm, we have to use L infinity norm. But this is the intuition that essentially tells you. So if we do the leading eigenvector computation, if there's a spectral gap in ground truth, and if the noise, the magnitude of the noise is not that big, then essentially we can recover the underlying ground truth, because if we have integrality constraints from the leading eigenvectors of X observation. Okay, so this is essentially a very simple algorithm, right? So leading eigenvector computation power method, which can be done very efficiently. So the step 2 is rounding the solutions through linear assignment. Okay, so for algorithm details, you can refer to those papers. So what's interesting here is the theoretic analysis, right? So in terms of the deterministic setting, right, you can show that it still tolerates a constant fraction of noise. But on the other hand, for clique graphs, the ratio is not 25%. Okay, it's slightly smaller than that. And this really shows that even though those approaches are all for recovering no-rank matrices, depending on the noise model, right? So one approach may works better a lot better than the other one. Okay, in particular, for adversarial noise, SDB formulation, which is computationally more expensive than the spectral technique, but on the other hand, it can tolerate more noise. Okay, in terms of randomized setting, the rate of the spectral map synchronization and SDP based approaches are similar. Okay, but they still differ in terms of a constant. Okay, but the rates are similar. Okay, so that is the insight here. Okay. And I also want to briefly cover some of the non-convex optimization techniques, right? So there are a lot of approaches for recovering non-rank matrices using iterative algorithms, and this has been applied for the synchronization problem. So the problem is that we are given pairwise differences, one real value along a graph. That characterizes the differences in the absolute values associated with vertices. A standard approach for translation synchronization, this is also used for them in ranking, okay, is to solve the so-called convex optimization problem, where the variables are xi, xj, that are associated with the graph vertices, and the observations of Tij associated with edges, right? So clearly, if we shift x by constant value, the objective function does not change. So we have to add an additional constraint that the sum of the values to be 0. Okay. So, however, this convex optimization formulation does not work very well for if the Tij, the noise, right? So the observation noise is biased. So what we did is to introduce the so-called truncated least square, which is motivated from reweighted least square. But the truncation really provides a powerful tool to throw the noise away. Okay. So what we do here is that we introduce the weight Wij in front of each objective term, but by doing so, we can make the objective to be quadratic, and then this admits a closed form solution, and we can use iterative algorithms for solving the least square. But after that, we can simply truncate. For example, xik minus 1 is the solution at the previous iteration, and the difference between Tij and the differences between xik minus 1 and xjk minus 1 is bigger than some threshold, that is also geometrically decaying, then we can just simply say, hey, this is observation is the noise, and we can set it to be 0. Okay, and this is a very simple algorithm, and in fact that we can analyze the exact recovery conditions, right? So in terms of adversarial noise, it can tolerate about 1/6. Okay, it's slightly better than spectral methods, but not as strong as SDP. Okay, and in the randomized setting, this kind of iterative algorithm becomes very difficult to analyze. Nevertheless, for example, if we have the bias, the observations, this iterative algorithm still can achieve a sub-constant, can tolerate sub-constant fraction of noise. Okay, but the optimal one should be a constant divided by a square root n times a log, potentially a polylog factor. Okay, so in other words, this analysis is not optimal. So I want to give a summary of no-rank based techniques. So essentially, we have the observation that is equal to the ground truth plus noise, and usually we have a recovery if in some reducer space, the spectral gap of the ground truth is bigger than a constant times x noise, right? So the constant depends on the optimization techniques being used, and but this kind of problem is not completely done. Okay, there are many non-convex techniques require further understanding. Okay. So far, we have studied deterministic procedures for solving map synchronization problems. An open question here is that can we learn this procedure? And we have some initial result along this line, right? This is called learning transformation synchronization, published at CVPL last year. So the motivation comes from the fact that, as I just said, the optimization problem that we are trying to solve are handcrafted, right? We have a handcrafted objective function, and we have handcrafted mapping constraints. Of course, we can derive some theoretic guarantees, for example, but there's a gap. Okay, for example, adversarial noise we can tolerate a constant fraction, But if there's some noise pattern in the noise, then we can freedom randomness, we can tolerate a lot more. But what about if the noise pattern is not a trivial, but shows some correlations? Then we actually don't know, right? But the question here is, can we actually for some specific applications such as 3D scene reconstruction from depth scans, the noise pattern may be persistent between the training set and testing set. So this motivates us to derive the so-called learning approach. So what we do here is quite simple. So first of all, we are trying to convert a synchronization problem as a reweighted least square synchronization, right? So essentially, we introduce the weights, right? So this is motivated from the work we just talked about. So we turn the we use the weight to encode to handle noise, right? So and we know that if we update the weights using the residues, then basically we can tolerate a constant fraction at observable noise, and if there's randomness, we can tolerate the other mode. Okay, so what we did in this work is to adjust the weight by using a weighting module. Okay, by using a rating module. So essentially, the idea here is that we give the input scans. The weighting module essentially takes into account whether these two scans, how these two scans overlap, right? So the noise pattern between basically the original geometry. So here we are talking about the transformation synchronization problem. And the weighting module also takes into global signal into account. For example, the spectrum of Laplacian and so on. So the weighting module also essentially tries, as I just said, right, combines multiple signals, how the distances among the overlapping regions, global signals such as spectral, the eigenvalues of the Laplacian, and we also have a few hyperparameters that essentially combine those signals into a final score for each pair of edges. We can learn this. And we can learn this end to end. The results turns out to be significantly better than using a handcrafted objective function. And we compared with a couple of state-of-the-art techniques for performing transformation synchronization, and both qualitatively and this really shows the benefit of using a neural network to encode the synchronization procedure. And this is not just getting started. I believe there are many ways to improve upon this. And we don't have time to discuss many other papers along this line. For example, uncertainty quantification. We barely covered a little bit transformation synchronization, transformation rotation synchronization, lower bounds, and it's recommended to read those papers. Okay, so far we have talked about the case where maps are given by permutation matrices or partial maps. More recently, in the deep learning era, we are interested in training neural networks. One view of neural networks is that there are also maps, right? So for example, in fact, you can think about neural networks can approximate any function between two arbitrary domains given sufficient data, right? And for example, monocular reconstruction, which takes input image as input output, a complete model, we can consider this a map that maps a space of images to the space of 3D models. Image captioning, mapping from the space of images to the space of natural language descriptions. Okay, so similarly, instead of just training a single map, a single neural network, we can consider joint learning of neural networks. Okay, the benefits are twofold. The first benefit is that it considering average more training data. Here is a toy example where we have two languages, and we want to train a machine translation that maps one language into another. But unfortunately, we don't have sufficient paired data. So to address this issue, very similar to the solving fractured surfaces example we showed at the very beginning, here we can introduce a multi-language that has rich paired data with the first two languages. And what happens here is that you cannot really compose the data set to get a rich analytic data set between the first two languages, because a sentence in Korean may have a translation in English, but this particular sentence may not have a translation in Portuguese, right? But on the other hand, we can train neural networks using the rich data, and the neural networks we can compose it, right, so into another neural network that addresses this issue. The second advantage, which is more appealing, is that it allows you to leverage unlabeled data for training. So here I give another toy example where we have a single input and single output. So what we typically do here is that we use a one representation to encode the input. On top of that, we train a neural network. And in this case, we can only use unlabeled data for training because we need to provide some constraints on the neural network. If we consider the joint setting where we have multiple representations of the input, and for each representation, we can utilize a neural network. So in this case, we can use unlabeled data for training. For example, non-weighted data as input, there are two paths, right? Each path, it will generate some prediction. Even if we don't know the ground truth for the prediction, we can ensure that constraint that the two predictions have to be compatible with each other, and that is unsupervised loss for network training. The challenge here is, of course, how to effectively define and enforce those constraints. When maps are given by dense correspondences or transformations of functional maps, we can use matrix representations of maps that lead to very effective low-rank based techniques. However, we cannot encode neural networks as matrices, right? So here we have to think about how to enforce those constraints in alternative means. Right, so I'm going to talk a little bit about the path-invariant networks, which is a framework for enforcing self-supervision constraints among a directed map network. So let me go back to the multilingual translation example. So here we can do some abstraction here. Essentially what happens here is that we have three nodes, each of which corresponds to a language, and we have three directed neural networks, each of which corresponds to a machine translation network. And two neural networks, we have rich paired data, that is F1 and F2, and F3 we cannot train directly, but we can enforce the constraint that F3 is equal to the composition of F2 and F1. We call this path-invariance, okay? Essentially that those are the composite network among two paths, and they should be equivalent to each other, right? So that is what happens. And I want to argue that this is somehow different from cycle consistency in terms of the constraints, right? The cycle consistency consists of cycles. In other words, the composition of the neural networks on our cycle should be identity. Okay, so but for the graph on the left, we don't have cycles, so they are not identical to each other. Okay, so of course, similar to the cycle consistency constraint, if we enforce the path-invariance constraint, first of all, we can define this, right? For all the path pairs that share the source and the target, along different paths, the compositions should be identical, but there are just so many path pairs, right, to consider, and it's impractical to enforce all of them. Okay, the idea here is that can we find a small subset of path pairs so that they can induce the path-invariant property among of the entire graph. So we will come back to this in a minute. But suppose we have a path-invariant spaces, essentially we can formulate this total loss for joint learning of neural networks, right? It has a supervised loss and also a unsupervised loss, right? In the language model, the supervised loss has two terms. right? One for each paired data, which paired data. And for the unsupervised loss, we have one term, right? That essentially enforces F3 is equal to the composition of F2 and F1, right? So that averages unlabeled data. Okay, so this is good, but the question is that how can we actually derive a small collection of path pairs? To do this, we need to define the so-called induction operations. So here we consider 3 of them: merge, stitch, cut, right? So those are the operations that under which the path-invariance property is preserved. Okay, the path-invariance property is preserved. Okay, and under those induction operations, so we have the main result essentially says that given a directed graph with n vertices and m edges, there exists a path-invariant basis with size at most n times m. Okay, so it's a polynomial size. The proof essentially utilizes the fact that a directed graph is a cyclic graph of strongly connected component, and we can use a vertex order to construct a path-invariant basis for that. Okay, so this also gives us a polynomial time algorithm for computing a path-invariant basis. To understand the path-invariant basis, let's draw some connection to another algebraic and a combinatorial quantity called the cycle basis on graphs. Okay, so essentially a cycle basis is a collection of cycles. If we encode each cycle using the edge indicators, then essentially all the other cycles linear combinations of the cycles in this cycle basis, and depending on the weights, like integers, binary integers, real values, and we can divide the cycle basis into different categories. Okay, the cycle basis generalized to the cycle consistency basis. So they're defined on directed graphs. So the induction operations are merge and stitch. And in a recent NIPS paper, we actually analyzed the cycle consistent basis in depth, right? We can show that the minimal size of cycle consistent basis is the number of edges minus number of vertices plus 1, and it's related to spanning trees. But the difference between path-invariant basis and cycle consistent basis, one difference is that we conjecture that given a directed graph, computing the minimal path-invariant basis is NP hard. Even though we have a polynomial upper bound, but computing the minimum one, we conjecture that is NP hard. And we also have another conjecture basis that says that testing cycle consistent basis, okay, path-invariance basis are also NP hard. Okay, you may want to ask what are the advantages of pre-computing a path-invariant basis. Instead, we can just randomly sample path pairs, right? Inspired from the success of stochastic gradient descent algorithms. In fact, there's 3 advantages, right? So the first advantage is that if we do random sampling, one may need to sample many exponentially number of path pairs to ensure the path-invariance property, right? So many non-path pairs, okay, except for very special graphs. Okay, so in general, if we do random sampling, there's no guarantee. Okay. Another advantage is that if we do random sampling, we end up with sampling many path pairs. There's also a cost of implementing one new path pairs. Okay, there's an overhead over there, right? So also the convergence of stochastic algorithm becomes slow. Okay. All right. So we have tried this on semantic segmentation of ScanNet. So here we use the map network with 7 representations and 3 for the point clouds and 2 for the volumetric representations, right? 1 input, 1 output. The message here is that even under different resolutions of each representation, neural networks tend to learn different features. Okay. So the message here is that another message experimentally, we show that using 8% of labeled data plus 92% of unlabeled data, this is equivalent to using 30% of labeled data. Okay, so this is quite encouraging, right? And this result is persistent when using a single neural network for testing, or we do ensemble among predictions of using different neural networks. Okay. So that is for network training, and we also compared this explicitly enforcing the graph theoretical constraints for optimization and the no-rank based relaxations. Okay. Here the message here is that on sparse graphs, this kind of explicitly enforcing the constraints explicitly along path pairs is better than just doing spectral relaxations or convex relaxations. Okay. One intuition here is that the sparse graphs, the spatial gap is very small. Okay. This kind of relaxation techniques work a lot better when the graph is dense. Okay. But on the other hand, for sparse graphs, if we explicitly enforce those constraints, we are not doing any relaxation. Okay. So that explains why this can potentially work better. Okay. Okay. So there are many future directions to explore. On the theory side, I think one direction is to consider joint optimization of maps, right? The maps between pairs of objects and enforcing map consistency, right? So we have a lot of techniques for doing this, but we don't have satisfactory theoretical understandings of those techniques. Okay, end-to-end learning for synchronization, and I believe there are many more works to be done in this region. Again, we also need to understand theoretically why this is definitely better than using handcrafted objective functions. Right, and in the last part of the talk, we talked about self-supervision constraints, and we also need to analyze them, right, particularly from the perspective of optimization. Okay, so that's all I have, and thanks for listening. And if you have questions, please drop me an email. I'm very happy to answer. Okay.